Good morning, everybody. Hope you're all healthy and safe at home. We are going to continue with our first module, section 1.1, on the definitions and terminologies related to a differential equation. So in the previous lecture, we had discussed, or we had dealt with the various types of differential equations and based on classification of differential equation and all. So in this whole study on differential equations, we shall be concentrating on finding the solution of a differential equation. Obviously, when we are given any equation or may name, like in polynomial functions also, we are familiar with the factorization and how to find the value of x and all. So in a similar manner, our aim in this study of differential equation is to find the solution of the given differential equation. So in this section, we shall discuss about various terms and various types of solutions and all which are present. So let's see what is meant by the solution. So first we shall be discussing about the solution of an ordinary differential equation. So any function phi which is defined on an interval I and possessing at least n derivatives that are continuous on the interval, which when substituted to the nth order ordinary differential equation reduces the equation to an identity, is said to be a solution of the equation on the interval. So that is, if we are able to find any function which satisfies the given differential equation. So if the differential equation is of third order, then a function satisfying this differential equation means it should have third order derivative, then only it will satisfy. So a function which possesses at least n derivatives and which are continuous on a given interval, a particular interval, we are discussing about the solution in a given interval, which when substituted into an nth order ordinary differential equation, which will solve or which will reduce into an identity form, is said to be the solution of the equation. Now we have to keep in mind the interval which is given in the previous definition. The interval plays an important role. So that interval in which the solution exists is sometimes called as the interval of definition or interval of validity, or it is also known as a domain of the solution. Okay, now this interval can be open, closed, semi-open, semi-closed, infinite, any interval is possible, but we should mention the interval of a solution when we are discussing about the concept of solution. So we shall see an example which is given in your textbook depicting the interval. That is, verify that the indicated function is a solution of the given differential equation on the interval. That is, the interval is given to us minus infinity to infinity, and we have to verify whether this function, we have two parts, a and b. So the equation, differential equation, is dy by dx is equal to x into y raised to 1 by 2. So what are we asked? We are asked whether this function, that is y is equal to 1 by 16 x raised to 4, this function is a solution of this differential equation or not. So how can we verify it? By substituting the value on both the sides, right? So if y is 1 by 16 x raised to 4, what will be dy by dx? It will be 4 into x cubed by 16, that is x cubed by 4. Now let us substitute this y in the right hand side. So x into x raised to 4 by 16 whole raised to 1 by 2, that is nothing but x square by root of 16 is 4. So x into x square by 4 is nothing but x cubed by 4. So both these sides are equal. And also there is no problem regarding this function in the given interval minus infinity to infinity, because it's just a polynomial. So polynomial are continuous, so there's no problem with this function. Similarly, let's see the b part. We are given y is equal to x into e raised to x, and we have the differential equation is y double dash minus 2y dash plus y equal to 0. So what is, we have to substitute and see whether this sum comes out to be 0. So if y is x into e raised to x, what will be y dash or dy by dx? That will be x into e raised to x plus e raised to x, right? By product rule, it will be x into e raised to x plus e raised to x. Now we have to differentiate it again. So x into e raised to x differential is x into e raised to x plus e raised to x, and we have the differential of e raised to x. So again we'll have one more term, e raised to x. So y double dash will be x into e raised to x plus 2 into e raised to x. Okay, so now we'll substitute this value and we'll check whether it is 0. So we can see that this is x into e raised to x plus 2 e raised to x minus 2 into y dash, that is x into e raised to x plus e raised to x plus x into e raised to x. So x into e raised to x minus 2x e raised to x plus x e raised to x. So that is becoming 0. All x into e raised to x gets cancelled. Then we have 2 into e raised to x and minus 2 into e raised to x. So that is also 0. And also this function x into e raised to x is properly defined or well defined in the given interval minus infinity to infinity. Now there is a concept called as a trivial solution, that is the solution y is equal to 0. If you put y equal to 0, if you put y equal to 0 in the first part, what is derivative of 0? That is 0 itself. X into 0 is again 0, so 0 is equal to 0. Again, if y was 0, then y dash is 0, y double dash is 0. So y equal to 0 is actually a solution which is defined on any interval, and that is a trivial solution. That is called as a trivial solution. So keep in mind what is meant by trivial solution. The trivial solution is nothing but the solution y is equal to 0. So that is how we can define the solution, or we can verify the solution and check whether the given function is a solution or not. And the function must also be true to, or it must be continuous in the particular given interval. Now next we are going to define the term called the solution curve. So it is just a simple definition. What is it? The solution, we have now stated that solution is nothing but a function, right? So the graph of that particular function is called as a solution curve. So the graph of a solution phi of an ordinary differential equation is called a solution curve. So keep in mind we are discussing only about ordinary differential equation. So the graph of a solution phi is nothing but it is called as the solution curve. Now since phi is a differential function, it is continuous on its interval I of definition. Okay. Obviously phi, the derivatives of phi must exist. So if phi is differentiable, it will be continuous also. Now you have to keep one note in mind, that is there will be a difference between the graph of the particular function and the graph of the solution. Why the graph of the solution? Actually it depends upon the corresponding interval which we are considering. Okay, but the graph of that particular function, that solution is a function, so graph of that function will be different from the graph of that solution. So you can see in example 7 of your textbook, okay, we are given the differential equation. Consider the solution, or consider, if you see in B part, consider the equation x y dash plus y is equal to 0. Okay, then y is equal to 1 by x is a solution of this. How can we verify that? That is x into dy by dx plus y is equal to 0. So how can we verify that y is equal to 1 by x is a solution? First we'll find y dash and we'll substitute in this and we'll see whether it is equal to 0. That was the previous example. So you guys can just verify it. So y equal to 1 by x is actually a solution of this differential equation. Okay, but when we say y is a solution, we mean that that function is that particular function y is equal to 1 by x is defined on the interval on which it is differentiable, and it satisfies a particular equation. That is, if you see the function, if you see figure 1.1.1a, the function y is equal to 1 by x, actually the graph is of this form. Okay, this function is not defined at the point x is equal to 0. It is not differentiable at that point. So it is actually, we have a asymptotic graph. Okay, So it is of this form, but as a solution which we are considering, this is particularly given in the interval 0 to infinity. In the interval 0 to infinity, y equal to 1 by x, that is a solution y equal to 1 by x has of the form, this part, that is only the upper portion. Okay, so the graph of a particular solution of an ordinary differential equation actually depends on the particular interval that we are considering. The original graph may be more than that, more structure or curves will be present, but of the solution it will be depending upon the interval. So this solution y is equal to 1 by x that we have considered in this example is defined everywhere except at any, it is defined in any interval which does not contain 0. So in any interval not containing 0 we can form the graph. So this figure is just depicting the solution y equal to 1 by x in the interval 0 to infinity. Okay, so that is the positive part, so that is the upper part. So that is the definition of our solution curve. It is you don't have to get much worried about it. It's just the graph of the given solution, that is, which is a function. And since the interval, we are concentrating on an interval of the solution, we have to just draw the graph at that particular given interval. So that's about solution curve. Now next we shall move on to the types of solution. So we are going to discuss about explicit solution. Okay, what is meant by explicit solution? A solution in which the dependent variable is expressed solely in terms of the independent variable and the constants is said to be an explicit solution. Okay, so what is a solution? Solution is a function, right? So the solution is said to be explicit if the dependent variable can be written as a function of the independent variable explicitly. Okay, it can be written in that form, that is y is equal to phi of x. If we are considering y as the dependent variable and x to be the independent variable, then y equal to phi of x or y is equal to some g of x, h of x, whatever it is, y should be equal to something. That is, the dependent variable must be expressed in terms of the independent variable. That is called as the explicit solution. Now we have another type of solution which is called as an implicit solution. So what is an implicit solution? A relation g of x comma y equal to 0 is said to be an implicit solution of an ordinary differential equation on an interval I, provided there exists at least one function f that satisfies the relation as well as a differential equation on I. So just now we had discussed about explicit solution, that is y is equal to phi of x. It is of that form. And what is implicit solution? It is actually a relation. Okay, it will be some identity or something like that. It is a relation g of x comma y equal to 0. That is called as implicit solution. That is, we cannot we will not be able to write y as solely in terms of the independent variable. Sorry. So sometimes g of xy equal to 0, that is a relation between x and y, will be actually a solution of the given differential equation. So we can see an example which is given in your textbook, which depicts this concept about the explicit and implicit solution. So first let's see what is of the concept of explicit solution. So you can see that many differential equations are given. That is, if we consider dy by dx equal to x into y raised to 1 by 2, we have done this. So we are just discussing the case of the examples that we have done, and if you note that in all the examples we were discussing about explicit solution. So dy by dx is equal to xy raised to y by 2. This is the differential equation. We know y is equal to 1 by 16 into x raised to 4 was the solution. That is, y is solely written in terms of the independent variable x raised to 4. Also, y equal to 1 by x is the solution of x y dash plus y equal to 0. and y double dash minus 2y dash plus y equal to 0, that differential equation has a solution y is equal to x into e raised to x. So in all the solutions that we have discussed so far are explicit solution, because in that the dependent variable can be written as a function of independent variable. Okay, but in most of the case, or mostly, we get a relation or an expression which forms the solution of the ordinary differential equation, so that is called as the implicit solution. So we have an example which is given to us, that is consider the differential equation dy by dx is equal to minus x by y. Okay, then we are going to verify that x square plus y square is equal to 25 is actually a solution of this. Okay, so how can we verify that? What I'm going to do is I'm going to differentiate this whole equation. Okay, when I differentiate this equation, I get 2x plus derivative of x square is 2x plus derivative of y square with respect to x, that is 2y into dy by dx, that will be equal to derivative of constant is 0. So if I differentiate this equation with respect to x, I get 2x plus 2y is equal to dy by dx into dy by dx equal to 0, or I can take this x on and y, the terms of x and y on the other side, so I'll get dy by dx equal to minus x by y. Okay, so we get that this expression, that is this relation x square plus y square is equal to 25 is actually a solution of the given differential equation. Okay, so not one thing, this is a non-linear equation. Why? This is actually, this expression contains y into dy by dx, that is the product of the independent variable and its derivative, so that must not be present in a linear differential equation. So that is just to recall the difference between non-linear and linear. It has nothing to do with the solution part. So this is an example of an implicit solution. Okay, now the figure 1.1.2 actually depicts the different solution also. An implicit solution and two explicit solutions are given. Implicit solution is x square plus y square is equal to 25. Now if we consider, if we solve this expression x square plus y square equal to 25 in terms of x, we get y is plus or minus root 25 minus x square. So this also actually, that is y is, again we are writing y as a function of x, right? So this also actually forms the solution of the given differential equation. So there is one more thing that we can keep in mind, that is, now we had considered x square plus y square is equal to 25, right? Is there anything important about 25? Actually there is nothing important about 25. It can be any constant because the derivative of constant is 0. So the general equation can be stated to be x square plus y square minus c equal to 0 will be the equation or the solution of the given differential equation. So we have seen that in the previous example, x square plus y square minus c square is a solution. It is a general solution of the given differential equation. So depending upon the values of c, we get many solution of that given differential equation. So we can discuss about the families of the solution. Okay, now a solution containing an arbitrary constant represents a set g of x, y, c equal to 0 of solutions, and that is called as a one parameter family of solution. Okay, so there is just one parameter c. Now if we are considering g of x, y, c1, c2, etc, cn equal to 0, that will form the n parameter family of solution. So for a particular just single differential equation, we can get infinitely many number of solutions, right? Depending upon the choice of the parameter. So if you see the previous example itself, x square plus y square is equal to 25 is a solution. We have verified that. Similarly, x square plus y square is equal to 4, x square plus y square is equal to 9. Everything will be a solution of that particular differential equation. right? So we can find infinitely many number of solutions of a particular differential equation. So that collection of solution forms a family of solution. Now among them we can consider a particular solution. That is, if the given solution is free of any arbitrary constant, then we say that it is a particular solution. Okay, so if you are considering the previous example, x square plus y square equal to c square or equal to c was a family of solution. Now if I put c is equal to 25, I get a particular solution of that particular family, right? Of that family I get a particular element or a particular member of that family. So x square plus y square is equal to 25, and there is no parameter in it. There is no c or c1 or c2 etc. in it. So any solution which contains no parameter, it is called as the particular solution. That is, we substitute the value for that parameter with some value. Okay, so that is called as a particular solution. Now we shall just see an example which is given in your textbook. That is, we are just considering the differential equation x double dash plus 16x is equal to 0. Okay, now this differential equation has a specialty. That is, if you consider x to be c1 cos 40 or x is c2 sin 40, both these, that is cos 40 and sin 40, both of them will satisfy the differential equation. You can verify it. Okay, so suppose x is c1 cos 40, then what will be x dash? X dash will be minus 4c1 sin 40. So x double dash will be minus 16c1 cos 40. So I'm going to substitute this. That is minus 16c1 cos 40 plus 16 into c1 cos 40, which is 0. Again, if I consider x to be c2 sin 40 also, I'll get the same values. I mean, I'll first x dash will be cos 40 minus 4c1 minus 4c2 cos 40, no, 4c1 cos 40, there is no negative sign, and x double dash will again be minus 16c2 sin 40. So if I substitute it in the given differential equation, again I'll get it 0. Also we can note one thing, that is, if I combine these together, that is, if x is c1 cos 40 plus c2 sin 40, then also it will satisfy this differential equation. So you can just verify it. Okay, that is, if I get two solutions of a particular differential equation, then their sum is also a solution of that differential equation. Okay, now just consider, let us look into one more example. Okay, that is example 10. Okay, consider the linear differential equation x y dash minus 4y equal to 0. Okay, then clearly y is equal to c into x raised to 4 will be a solution. Okay, you can verify it. Okay, y is equal to c into x raised to 4. So here there is just one parameter. So this is a one parameter family of solution. So y is equal to c into x raised to 4 is a solution of this differential equation. Okay, now if I consider y is equal to minus x raised to 4 when x is less than 0 and x raised to 4 when x is greater than equal to 0, this is also a particular solution, right? This is also a solution. I am putting c is equal to minus 1 and for whenever x is less than 0, and c is equal to plus 1 whenever x is greater than equal to 0. So this is also a member of this is also a particular solution of the given differential equation. I am substituting values for c, but this solution cannot be obtained, or it cannot be a part of this family. Why? This particular solution, that is why I am defining it with a break, right? So this particular solution cannot be obtained as a member of this family, right? Because I will have to substitute two values for c at the same time. That is not possible, right? So y is equal to, but this is a solution of the differential equation. Y equal to minus x raised to 4 when x is less than 0 and x raised to 4 when x is greater than equal to 0 is actually a solution in this particular of this differential equation in this particular interval. Okay, but we cannot obtain this particular solution, that is y expressed in this form, as a member of this one parameter family of solution. So that is when we are going to discuss about the singular solution, that is a solution which is different from the given family. Okay, that is called as a singular solution. So such an extra solution, so there are possibilities to find such solution. So such an extra solution is called as the singular solution. So sometimes a differential equation possesses a solution which is not a member of the family of solutions of the equation. So that solution cannot be actually obtained by giving any particular value for the parameter. Okay, we have seen in the previous example we had to give two different values for the parameter, then only we will obtain that particular solution. So such a solution which cannot be obtained from the member, or which cannot be obtained by substituting a value for the parameter, is called as a singular solution. So as we have seen in the previous example, it is clear about what is meant by singular solution. Now again we can see one more example which is given in your textbook to make that concept about singular solution a little bit more clear. So what do we have? We are given the differential equation. Consider the differential equation dy by dx equal to x into y raised to 1 by 2. Okay, then y is equal to 1 by 16x raised to 4 is a solution. We have seen that. Also y is equal to 0 is also a solution, right? Now if we consider when we solve this, this is like verifying the concept, right? So when we actually solve the differential equation dy by dx equal to x into y raised to 1 by 2, the parameter or the set of solutions which we obtain is y is equal to 1 by 4 x square plus c whole square. Okay, this is this will be the family of solution that we obtain. That is, we shall be dealing with determining the solution in the coming sections, that is in section 2.2 and all. We shall find we shall discuss about methods to determine the solution of a given differential equation. So far we have not found out the solution. We were given solutions and we have just verified it. Okay, that is just to keep in your mind or put in your mind the various terminologies related to solution. So here also we had seen that y is equal to 1 by 16x raised to 4 was a solution of this differential equation. But when we solve when we find the solution, we can find the family of solutions, and that is nothing but y is equal to 1 by 4 x square plus c whole square. Okay, so when we put c is 0, I get 1 by 4 x square whole square, that is nothing but 1 by 16x raised to 4. So when c is equal to 0, I get this particular solution. But is there any possibility or any value for c such that I get y is equal to 0? It is not possible until and unless x is put, x and c both must be put to 0, right? So this y is equal to 0 is a solution of this given differential equation. So y equal to 0 forms a singular solution. We cannot obtain this solution, that is, we cannot obtain the trivial solution y equal to 0 by substituting any value to c. Okay, but if you put c is equal to 0, I get this particular solution. Alright, so that is called as a singular solution. That is, it will be completely different from the family of solutions that we obtain once we solve the differential equation. Now we shall discuss a small topic more and we shall wind up with our section, that is our system of differential equation. That is, we'll be given more than one differential equation and we'll have to solve it. Okay, the system of ordinary differential equation is two or more equations involving the derivatives of two or more unknown functions of a single independent variable. Okay, it is we'll have more than one equation involving the derivatives, okay, of two or more unknowns and all. So if you consider this dx by dt equal to f of, it is a function of t, x and y, and dy by dt is a function of t, x and y again. So x and y are the dependent variable and t is the independent variable. So there is just a single independent variable and more than one dependent variable, and we are having two set of equations. Okay, sometimes the solution of such a system will be a pair of differentiable functions. That is, we'll get, if we solve this, we'll get the value of x as well as y, right? X will be a function of t, y will be another function of t. Okay, now we shall discuss that in the exercise. And also we have such type of differential equations also, that is more than one differential equation which we have to discuss and we have to solve for x and t. For there will be, if there are more than one differential equation, then clearly there will be more than one dependent variable. So we'll get the solution for both those dependent variables in terms of the independent variable. So that is the system of differential equation. So that's it for today's session. Thank you. Stay home and stay safe.